So, chapter 11. In chapter, this is really a continuation of chapters 9 and 10. So we saw that to go from a function to its derivative, we use this operation of d dx, right? We're doing the derivative, goes from f to f prime. If we'd like to now be able to recover the original function from a derivative, stop talking please everyone. If we'd like to recover f from f prime, the operation we use is called the integral. We call that process anti-differentiation. That S symbol is called the integral. But there's one little catch in this process. Let me just present to you why there's a little catch. Let's say f of x was 2x plus 3. So what is f prime going to be? 2 plus 0, right? Now, if I want to then do the antiderivative of 2, well, I can follow that same, or the reverse of the same power property that we'd use to do our derivatives. So I can take, here I'm going to think about 2 as 2 times x to the 0, because 2 is 2 times 1, and 1 can be x to the 0. And then I can add 1. Instead of subtracting 1 to the exponent, instead of multiplying by that exponent, I can divide by my new exponent. But what will never be recoverable? The 3. So anytime we do this anti-differentiation process, we're going to tack on a plus c at the end to acknowledge that, hey, there could have been a constant attached to this also that gets destroyed when we take the derivative. We'll never be able to recover that without some additional information about our original function. So to account or acknowledge that, we're going to put a plus c at the end. The c is just representing a constant. All right, so let's run through a couple of examples with you guys. So the directions ask us to find an antiderivative with respect to x for each of the following terms. So the symbols that I use to represent that I'm doing an antiderivative is this integral symbol. So remember what we did before. I'm going to, since there's no x there, I'm going to think about it x to the 0. And then because we're doing an antiderivative, instead of subtracting 1 from the exponent, we're going to be adding 1. And instead of multiplying by that exponent, we're going to be dividing by the exponent. But really, what's that just turn into? x. And anytime we do an integral or an antiderivative, you could use those two terms somewhat interchangeably. What do we need to include? Plus c. To represent that there could also have been some constant there that got obliterated when we took the derivative. Okay. What's the antiderivative of x going to be? Remember, we're going to add 1 to the exponent, so the new exponent should be 2, right? And then we have to divide by the new exponent. So it should be over the new exponent, 2, and then plus c at the end. You guys starting to feel like you're getting the hang of using this rule? How about if I do x squared? What should I write here? Over 3 plus c. Good. Our last one was x to the 4th. What's the answer here going to be? We feeling okay with this process? These are like the simplest of the simplies, but it's okay. What the heck? Hold on a second here, folks. This is oh, this is so dumb. This is a terribly worded question. I'm going to acknowledge here that the wording of this question, apparently what they wanted you to do was something different than what we had done. It's super dumb. I'm not going to do it. I'm just moving on. I'm going to acknowledge that we did this problem wrong according to the book. But like the wording of their question was so bad, I can't imagine anybody actually wording a question like that. It was really unclear, and I don't know what the point of the question that they were trying to get you to do here would be at the point in which they're presenting it to you. So we're going to just do what we did and say, okay, that was some practice doing the integral, which I think was good practice. So in general, the formula that we were just using there was this, right? That if I do the integral of x dn dx, I get 1 over n plus n times x dn plus 1 plus c. And that works for integer values of n, where n is not -1. We have a whole separate antiderivative rule when if you have x to the -1, that's not covered in this course and you would not be responsible for. Additional rules for integrals that would be helpful to you. The integral of a constant k times a function f of x. We can pull that constant to the front. And then if I have the sum or difference of two functions inside my integral, that my integral distributes to each of the, I can distribute my integral across the addition or subtraction symbols. Everybody's okay? Keep in mind, cannot distribute an integral through multiplication or division. All right, these are going to be your three main anti-differentiation rules. So let's cruise through some examples here. So I'll start so if I want the integral of 4t dt, I'm going to, 4 is a constant, so I can just come out to the front, apply my antiderivative rule for t. So I'm going to add 1 to the power and then divide by the power plus 1. So that becomes 2t squared plus c. What do you guys think? Is that okay? All right, who can do part B? What should I do first? Pull the 3 out front. Good. Then what? You could just say 3 there too as well. That would be okay. And that simplifies then to just x cubed plus c, right? Okay, I don't think we're going to do all of these because C and D I think are pretty similar to what we've just done. Let's skip ahead and maybe go to do E. That looks like a good one. So E, the first thing I'd want to do is distribute my integration. And then I can take the 6 and move that out front, as well as the 2 and move that out front. Questions on how I did any of that? Okay. G looks like a good one. Does that scare you with the A there? What do I do with that? Yeah, it's just a constant. Not 8 of, yeah. And then you could just leave it like that, I guess, or you call it ax cubed over 3, whatever. Let's do I maybe. You guys are okay with me just kind of skipping along here a little bit, right? Okay. There's a lot of examples here. First thing I would do here, what do you notice about the thing we're trying to integrate? Yeah, the fraction, but specifically what about this fraction's going to be the issue? The variables in the denominator. Yeah, so what do we do with that? I'm going to make it a negative exponent. Everybody's cool? So now we distribute our integral, and I'm going to pull the constants to the front all in one step. Is that okay? All right. So when I do the integral of negative x to the negative 2, I'm going to end up with negative 5 over 2, and then that's x to the negative 1. So maybe I put it back there. I could also just write it as x to the negative 1. That's not incorrect. Should try to get that negative sign in my circle. Is that okay? No big deal there. Right, the key is just remembering to take care of or simplify the beginning piece appropriately so we can use our rules. What am I going to do here? I'll give you a hint. I'm going to write that fraction with a common denominator as two separate fractions with common denominators. That's going to reduce down to 1 over x cubed. So I can write that as x to the negative 1. And the other one I can just write as 200x to the negative 4. Everybody's okay with that? We use the same trick when we do derivatives, right? Okay. What do I get when I do the integral of x to the negative 3? Great. And what do I get when I do x to the negative, or the integral of x to the negative 4? So we'd have negative 1 over 2x squared plus 200 over, I should say minus, over 3x to the third, and still my plus c at the end. Now, in some cases, if you're giving additional information about your original function, we will be able to solve for c. So let's see an example of where we can do that. So if I know one point in the original function, I can solve for the c specific to that situation. So it says a skydiver's vertical velocity is modeled by the function V of t equals negative 9.8 t, where V of t is our vertical speed in meters per second, t is the time in seconds since you jumped out of the airplane for t between 0 and 10. And then it says the aeroplane has an altitude of 3,900 meters at the instant the skydiver jumps out. What is that statement saying in terms of V of t? Great. V of 0 is equal to 3,900. Oh, I'm sorry, not V. S of 0, right? The position function, right? Because recall we had S of t, we take the derivative, we get V of t, we take the derivative, we get A of t, right? Position, velocity, acceleration. So if we go back, we're going to have to be integrating, right? So our S of t is going to be the integral of V of t dt. We're told V of t is negative 9.8 t. Everybody okay to there? And we're told S of 0 is going to be 3,900. So does that tell me C's got to be? $3,900, right? So my real function then for this specific situation is that that's my answer for part A. For part B, what should my unit be? We started out here in meters per second. We're backing up, doing the integral. Should be in meters, yep. The way to think about that is, and we'll get to this topic in the future, but if I think about the graph of this function, it's like that, right? Negative 9.8 t, it's just like, oops, sorry, should be like that. Nope, sorry, this way. Well, like, I guess it's plus 39, it's like that. Let's say that. So this axis is t. This axis is v in meters per second in seconds. The integral kind of corresponds to the area under that curve. If I'm going to take meters times seconds, I end up in, or meters per second times seconds, the unit is meters. We'll talk more about area under the curve representing an integral in future sections, but that's kind of where we're heading. Okay, so that was meters. And then part C asked to find the altitude of the skydiver, 1, 5, and 10 seconds. Well, like, dude, come on, all we're doing is doing stuff like this, right? And I'm not going to bother with the calculator. Yes, sir. But it's just like plugging and doing some chugging, you know what I'm saying? No big deal there. Okay, and we can do this. Oh. Now, rather than doing this specifically like in a specific story problem situation, we can think about this in just like a generic situation. So again, if it says find the specific antiderivative for the given boundary condition, the boundary condition they're talking about is just like some point on the original function. But specific means we want the value for c, right? If it's a general antiderivative, plus c is good. Specific, it means we want the value for c. So we know f of x is going to be the antiderivative of f prime. So filling in, I can distribute the integral and pull out the coefficients. So that's my function for general function for f of x. But I have that f of 1 has to equal 60. That's 25, and another 25 is 50. So when I subtract that to both sides, I get c is 10. So f of x should be 25x squared plus 25x plus 10. How do you guys feel? Okay there? Again, it's really the same process as before, just like we've added in this one extra step where you have to solve for the c. But it's like whatever, you know, just I can solve for c, that's no biggie. All right. One more example, story problem, kind of doing the same thing, but presenting as a different context. A factory has modeled the marginal cost of producing sunglasses as C prime of n equals yada, 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 where C prime of n represents the additional cost in US dollars for an additional pair of sunglasses, and n is the current level of production in thousands of sunglasses per month. The factory is currently producing 1,000 pairs of sunglasses per month at a cost of 50,000 US dollars. Oh, yep. Thanks. That's a good point. All right. Our derivative is cost per pair of sunglasses, right? Everybody okay with that? Oops, they used n here, not x. But what is our n measured in? So I just took the unit for my derivative and multiplied it by the unit for n. And the result gives me my unit for c of n. Everybody's okay with that? It's that area under the curve idea, right? If I just take the y and the x and I multiply them together, it should give me the unit for the antiderivative. The next is it asks for a function for c of n. So I know that's the integral of c prime of n dn. And I'm going to just distribute through my integral and pull out my constants. So that's my general function. Now, what is that telling me? The factory is currently producing 1,000 pairs of sunglasses per month at a cost of $50,000 US. Tells me C of 1 should equal 50. Remember that n is measured in thousands of pairs of sunglasses, and we said C of n was going to be in thousands of dollars. So to solve for my constant then, let's see, I have 95 minus 65 is 30. I subtract 30 from both sides. My constant is 20. And then lastly, it says find the minimum total production cost and then the corresponding production level. So how do we find the minimum for a function? I need the derivative equal to 0. So to solve for that, I can graph this. So if I graph my derivative, that was 45n squared minus 130n plus 40. And this didn't give me a range here. That's okay. I know that x is the number of sunglasses. So I'm just going to go 0 to 10. So that's like 1,000 to 10,000 sunglasses. That seems appropriate. And y is going to be like my cost per, and I don't know what this is going to be. I'm going to do like negative 100 to positive 100. It's a rate though. We saw, yeah, so I don't really know. Okay, look, I have 2 zeros there. It looks like at 1 and 2, but I'll confirm that. Actually, which one do I want? The first 0 or the second 0? Which one is going to be the one I'm looking for? If I'm looking for a minimum, function needs to start moving from decreasing to increasing, right? So I want the part where I go from negative to positive. I want this second 0. So I'm not even going to bother with finding that first one. Is everybody okay with that? And then the production level would just be C of 2. Which again, I could plug that in by hand, or what I'm going to do is I'm going to type the equation in here and then just do like y2 of that. So the minimum is at 2,000 pairs of sunglasses, and the cost would be $40,000. You guys cool? You could have also graphed this function and used the minimum command on your calculator and done it 2 for 1. But I went and did it that way because it was reminding you of what we did in chapter 10. All right. So in the previous section, we saw that this is true, right? This is what we did. We took a derivative, we did the integral of it, you recover the original function plus some constant. This is sometimes called an indefinite integral. We say that it's indefinite because of the plus c piece. Alternatively, we can do what's called a definite integral. So if we want to integrate, say, from values a to b, well, that would give me like this. And look what happens to the c's. What's going to happen to them? They just cancel out, right? So this rule right here is called the fundamental theorem of calculus, and technically this is part 2 of that fundamental rule of calculus. Apparently your textbook does not think part 1 is worthy of them telling you what it is, but I will. Get ready. That's part 1. What is that telling you, really? Derivatives cancel out integrals, and integrals cancel out derivatives. Like the process of integration cancels out a derivative, or the process of taking the derivative cancels out an integral. That they're inverse operations of each other, just like a log will cancel out an exponential, and an exponential cancel out a log. Like a square will cancel out a square root, or square root cancels out a square. That's basically all it's saying. Or good enough for us, right? Maybe there's a little bit more subtle going on there, but not so much. All right. So let's see, how do we do a definite integral here by hand? So I approach this the same way I did before. I'm going to pull my constant to the front. I'm going to do my antiderivative rule. And then I'm going to draw a vertical line and write 0 and 2. Those are the bounds of integration again. So the 3's cancel. So what I'm going to have then is x cubed, where I plug 2 in, minus x cubed, where I plug 0 in. My answer is 8. Want to see something wonderful? Yeah. You can do this on your calculator. So if you have your calculator with you and you'd like to follow along, let's just kind of show you how we can do that. I think the easiest way to do this on your calculator is go ahead and type the function that we're integrating into y1. So into y1, I'm going to type in 3x squared. After that, I'm going to exit to the main screen and press Math. And I'm going to scroll down to command 9, which says fn int. So there's my integration symbol. So in the bounds, I'm going to type 0. I'll type 2. Inside the parentheses, I'm going to put y1. And at the end where it says d, I used x's in my formula, so I'm going to put an x there and then press enter. Yes, sir?
Could you just put like 6x there?
You could type the function in there directly also. If you have a bunch of them to do with the same function, though, or if the function is long and complicated, I think it's often easier to put it in this way, but you could certainly type the function directly. So again, what Gavin was asking, could I do 0 to 2 and just put the 3x squared right here directly? You absolutely can do it that way. It's just a matter of like what else you have to do in that problem, right? So if I have to graph it or do something else, or if I have to do that a bunch of times, oftentimes I'll put it in the y1 spot. All right, how do you guys feeling here? So far, so good? Let's skip ahead. Let's do D, and then we'll do the next set of examples or talk about the next idea here. So again, could I do this all in my calculator? I acknowledge, yes, that I can. I'm just not going to for the sake of exampling. Is that okay with you guys? So I'm going to have 3x squared, but instead of the x, I'm going to plug in the -2. Then minus, and I have to be careful here. Because I have like a quantity going on here. So I have to make sure that that subtraction is going to apply to the entire function. This is a super common mistake when students do this by hand, but really, should you ever do a problem like this by hand? On the IB exam, you want to make sure you're doing a problem like this on your calculator. Never do this by hand. Just type it in your calculator and press enter. And you're like, Mr. Kulik, this is really dumb. I'm like, hey, this is what they want you to do. They literally want you to do this. -4 squared is 16 times 3 is 48. And then 2 times -4 is -8, and then that's going to be +8. So that's 20 minus 52, so -32 or something. Yep. And we did this, and I want to point out to you that even if we don't know the anti-differentiation rules for how to do this, that doesn't matter. You can still type this crap in your calculator and press enter. So notice that if we tried to simplify this piece over here, we'd end up with 1 over w. That's w to the -1, so our power rule antiderivative doesn't work on that. You need a different derivative rule. Or this one where we have like a function 2x inside of another function like e to the x. I don't know how to do that either. Doesn't matter. Your calculator will handle it as long as it's definite integral. So again, whenever you see a definite integral, don't do it by hand. Use your calculator. That is what the IB people want you to do. They don't want you to do it by hand. And look at that goofy decimal we get there. That is okay. That can happen. Because in fact, the integral of that involves a logarithm. That's why you're getting the kooky decimal. You would never need to know that for the IB exam. But like, that's all it is. So rounded to 3 sig figs would be 59.5, right? And that's no big deal. All right. We'll do one more story problem example, and I'm done with 11.2, and that'll cover us for today. Sound good to you guys? Okay. It says a tank containing 10 cubic meters of water is draining. The change in water volume is given by dV/dt equals yada, 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 where t is in minutes since the tank has started draining. Find the change in volume of water in the tank in the first 3 minutes. So the volume going from 0 to 3, because it's the first 3 minutes. So this is a calculator problem. I'm not doing it by hand, especially with some of those cuckoo numbers in there. 0 to 3, 0.0002 x minus 0.5 dx. So I have approximately negative 1.50. So it means we've lost 1.5 cubic meters of water over those 3 minutes, which makes sense because it says the water's draining out of it, right? So a negative value there makes sense. Find the amount of water that drains from 4 to 8 minutes. Well, that's easy enough. So I'm just going to press second and enter to retype the thing and just change that from 4 to 8. So I got about 2 cubic meters have emptied out of that thing. And I guess here we should be a little bit careful. Notice the first one wants the change in volume, and the second wants the amount of water. But if here it's just asking for the amount, so really we want like the absolute value of this, right? Since it's asking for an amount can't be negative. Like, what amount of oranges did you get from the store? Can't come back and tell your mom got -3 oranges. That doesn't make a lot of sense. And the last one says, find the time in which the tank will be empty. Let's see, will our calculator do this for us? I hope it will. All right, so I'm going to type into here into y1, I'm going to type the derivative that it gave me. And then the next one, I'm going to do the integral from 0 to x of y1 dx. And I'm going to see what I get there. I'm going to reset that from -10 to 10. But I'm going to extend that out to be like 20 or something. Because I saw after 8 minutes, we only lost 2 cubic meters. I still have 10 in there, so maybe I have to really extend that out. So maybe I made that like 50 or something. Let's hit graph and see what I get here. Okay, here's my thingy-majigger. Oh, I'm so dumb. That's okay. I'm not so dumb, just normal dumb. So I'm interested in where this integral from 0 to x dv dt is equal to -10. That would indicate where it's empty. So I forgot to type in the -10 to find the intersection. That's what I meant when I said I'm so dumb. I got excited about like, ooh, can I get the calculator to graph this the way I wanted to? And there's my piece. So intersect, first curve, second curve, guess. And it's thinking. Yep, about 20.1. Oops, and those are minutes. Because it said X, or the T was in minutes. What do you guys think? Cool.
Cool.
All right, you guys should do the 11.1 and 11.2 homeworks for Sunday's problem set. My hope is to finish chapter 11 on Friday this week. And I was going to ask you guys, do you want to do a chapter 11 test? Nobody wants this?
We do no more tests. No.
Well, we're going to do the 10.
We have a 9.
The 9 and 10 test we're doing.
What?
But do you want to do a chapter 11 test?
I think we can pass that.
Yeah, I don't know about you, but
What if it's in class with a partner, an open book?
I
Would-
don't even think I
would-
can do that.
Do you want that? Hey, listen, all I'm trying to do,
9 and 10.
all I'm trying to, I'm just trying to give opportunities that nobody feels like, ooh, I would like one more good grade in the grade book before the end of the semester. Well, we're doing 9 and 10 the regular way. But I'm like 11 is one where like, it's at the timing of such like, I don't think we really need to do it. We could just start talking about the exam, IB exam, and doing targeted review of that. But if people are thinking like, hey, I'd like another good test grade in here or something, you guys think on it. We'll talk again about it on Friday,
I
right?
do need a good test grade. If it's like open book and partner,
Yeah, for 11,
then that would be a double.
because it could be your doubler
It
too.
could be your doubler.
Yeah. So just think on that. You don't have to make any decisions till Friday.